Hello, my name is Lucas Rodriguez Chiappetta. I'm a part of the Research and Chemistry program at the North Carolina School of Science and Math in Durham, and my project is titled The Design, Synthesis, and Evaluation of a Small Molecule Dihydrofolate Reductase Inhibitor for Psoriasis Treatment. Psoriasis is a chronic autoimmune disorder that affects roughly 125 million people worldwide. Psoriasis leads to stress, anxiety, and a lowered self-image. As a result, it degrades the life of those who possess it. At its core, psoriasis is a result of an overactive immune system where keratinocytes, which are cells that trigger inflammation, play a crucial role in the development and progression of the disease. As they proliferate rapidly, the epidermis thickens, which leads to the scaly patches that is seen in Figure 1. Some existing treatments are DHFR inhibitors, which is dihydrofolate reductase, and then antifolates. Dihydrofolate reductase reduces dihydrofolate, which is DHF, to tetrahydrofolate, which is THF. THF is essential for nucleotide production, as it is a carrier for one carbon unit required for the synthesis of purine, which is a precursor of DNA. Thus, inhibiting dihydrofolate reductase prevents the formation of THF, thereby limiting DNA replication and cellular proliferation, which helps to treat psoriasis. Due to this, DHFR is a likely candidate to be targeted for the treatment of psoriasis. Some existing treatments are toxic and require active transport. These are folate derivatives like methotrexate. Most of these are known as classical inhibitors, which have large amounts of hepatotoxicity, causing acute and chronic liver damage and cellular resistant issues. Due to this, the need for less toxic therapeutics is essential. Research has introduced non-classical antifolates, which are one subgroup is propargyl linked antifolates. PLAs show promise as their mechanism differs from methotrexate. They enter the cell through passive diffusion, which means they do not experience the same cellular resistance issues. On top of this, the charged aspect of PLAs makes it to where they are less recognizable by efflux pumps, so are they less readily expelled from cells, which also helps with cellular resistance issues. This project aims to computationally design, synthesize, and evaluate a small molecule dihydrofolate reductase inhibitor with increased binding affinity, reduced toxicity, and lower cellular resistance relative to various non-classical antifolates for the treatment of psoriasis. My project is split into three parts. The first is a computational design, the second is synthesis, and the third is testing. For computational design, I started with about 60 possible drug candidates using a purine-like structure. These candidates did do good, but their synthesis was too difficult for us to pursue. Due to this, we had to pivot in the direction of doing a readily accessible scaffold. 5-fluoro-1-propargyl uracil was selected to be that scaffold due to its synthetic accessibility and a built-in propargyl linker. The propargyl linker is very essential to the project as it is what helps with the cellular resistant issues. A variety of compounds, both iodine and bromine, were linked to the 5-fluoro-1-propargyl uracil, which is seen in Figure 4, and then docked to dihydrofolate reductase in Schrodinger's Mayaster suite. 6 of them showed promise with a better docking score, which is how well the small molecule binds to DHFR, QP-log-Hg, which is measures the potential for cardiac toxicity, and then percent human oral availability, which is how well the drug will absorb into the bloodstream. Figure 5 shows a possible aerobromine that could be linked to the 5-fluoro-1-propargyl uracil. Here is the computational data. The first two compounds are some that I created in Schrodinger itself, bromohydroxy and bromobenzene. And then UCP-162 and trimethoprim are two existing non-classical inhibitors that have been tested and synthesized and tested. So a more negative docking score is better, which means my compounds are outperforming the existing non-classicals by a decent margin. And for this reason, bromohydroxy was selected for synthesis due to its good docking score, its good QP-log-Hg, and its good human oral availability. Anything higher than 80 is good for oral availability, and then around 5 is also good for oral availability or for QP-log-Hg. For synthesis, I found a cross-coupling reaction called Sonogashira, which provides a synthesis where carbon-carbon bonds are formed between an aerobromide and a terminal alkene with a palladium catalyst paired with a ligand. In this case, the ligand was triphenylphosphine. And then it also has a copper co-catalyst, which in this case was copper 1 iodide. The aerobromide was 5-bromohydroxyacetophenone, and then the terminal alkene was 5-fluoro-1-propargyl uracil. And Figure 7 shows the final product, which I wanted to produce as my small molecule inhibitor. Here is the actual images from synthesis. Figure 8 shows the experiment setup. This was done with a nitrogen balloon to ensure an inner atmosphere because the palladium would oxidize in normal atmosphere. Figure 9 shows a close-up of the actual compound stirring and heating. And then figure 10 shows TLC analysis. TLC was taken over the span of a couple of days in the morning and the afternoon to see the changes that was happening with the compound. And TLC did confirm that something was going on and something was being changed. Essentially, what I did for the synthesis was I just put everything into that one vial, and then it stirred and heated for around 2 days. The future steps I want to pursue are to characterize my compound with nuclear magnetic resonance, specifically carbon NMR. I want to purify the compound with chromatography, and I want to test it with a DHFR inhibition assay and an E. coli toxicity assay. I want to give special thanks to Dr. England, Dr. Bruno, Mr. Lopez, my RChem peers, my SHRIP TAs, Kate and June, the NC Systems Science Department, Luke Malta, and the NC System Foundation. Thank you.